Today's challenge is to count unique email addresses, but there's a catch. Email providers have some special rules for how they treat dots and plus signs. Take a moment, what would you do to figure out which emails are truly unique? Alright, let's break down this problem. We are given a list of email addresses, like a list of text strings. Our goal is to figure out how many truly unique email addresses there are, after applying some specific rules. The rules are, first, for the part of the email before the @ symbol, which we call the local name, any dots should be ignored. So, john.doe@example.com is treated the same as johndoe@example.com. Second, also in the local name, if you see a plus sign plus, everything from that plus sign onwards should be ignored. So, john.doe plus alias@example.com is treated the same as john.doe@example.com, which, because of the first rule, is also the same as johndoe@example.com. The part of the email after that symbol, called the domain name, is always kept exactly as is. It's never changed. So, example.com is always example.com. We need to count how many distinct, final email addresses we end up with after applying these rules to every email in our input list. Let's look at an example. If we have test.email plus alex@leetcode.com, applying the rules, the dot in test.email is ignored, so it becomes test email. The plus sign and everything after it, plus Alex, is ignored. So, the local name becomes test email. The domain LeetCode.com stays the same. The final normalized email is testemail@leetcode.com. Now, consider test.e.mail plus bob.cathy@leetcode.com. Again, ignore dots, test email. Ignore plus and everything after, plus bob.cathy is ignored. Local name becomes test email. Domain LeetCode.com stays. This also normalizes to testemail@leetcode.com. See how these two, despite looking different initially, become the same unique address? Finally, test email plus david@lee.tcode.com. Local name test email has no dots to ignore, and the plus sign and everything after it, plus David, is ignored. So, local name is test email. Domain lee.tcode.com stays. This normalizes to testemail@lee.tcode.com. Notice this one is different because its domain is different. So, from our 3 example emails, we end up with 2 unique addresses, testemail@leetcode.com and testemail@lee.tcode.com. The problem constraints tell us we might have up to 100 emails, and each email string can be up to 100 characters long. This means we're not dealing with a massive amount of data, but our solution still needs to be efficient enough to handle these string operations. The most obvious thing to try first is to simply process each email one by one and keep a list of the unique, normalized emails we've seen so far. Here's how that would work. We start with an empty list. Let's call it our unique addresses list. We take the first email from our input list. We apply all the normalization rules to it, ignoring dots in the local name, ignoring everything after a plus sign in the local name, and keeping the domain name as is. This gives us normalized email string. Now, we need to check if this normalized email string is already present in our unique addresses list. To do this, we would go through every single email currently in our unique addresses list and compare it to our newly normalized email. If we find a match, it means we've seen this unique address before, so we don't need to do anything else for this email. If we go through the entire unique addresses list and don't find a match, it means this is a truly new unique address, so we add it to our unique addresses list. We repeat this process for every single email in our original input list. Once we've processed all the input emails, the final count of items in our unique addresses list will be our answer. Now, why is this approach considered brute force or naive? Because of that checking step. For every single email we process, we might have to compare it against all the unique emails we've found so far. If we have n emails in our input, and each email has a length of L characters, normalizing each email takes some time proportional to L because we're scanning the string. But then, to check if it's unique, we might have to compare it against up to n other strings, and each comparison also takes time proportional to L. So, for each of the n emails, we do roughly n comparisons, each taking L time. This means the overall time complexity becomes roughly n multiplied by L, or n squared times L. This can get very slow if n is large. The space complexity, meaning how much extra memory we use, would be proportional to n multiplied by L, because in the worst case, all emails are unique, and we store all n normalized emails, each of length L. The key insight to optimize this problem is to realize that we don't need to repeatedly search through a list to check for uniqueness. Instead, we can use a special data structure that's designed for exactly this, a hash set. Think of a hash set like a superfast, magical collection of items where you can instantly ask, have I seen this item before, or add this item to my collection. It's much faster than manually checking every item in a regular list. The reason it's so fast is that it uses a technique called hashing to quickly determine where an item should be stored or found, avoiding the need to scan through everything. So, our optimized approach will be, first, we declare an empty hash set. This will be our collection of truly unique, normalized email addresses. Then, we go through each email string in our input list, one by one. For each email, we need to normalize it according to the rules. Let's walk through the steps to normalize an email. First, we need to find the position of the symbol in the email string. This symbol separates the local name from the domain name. We can find its index, let's say @index. Then, we can extract the local name, which is the part of the email string from the very beginning up to, but not including, the @index. We also extract the domain name, which is the part of the email string starting from the @index all the way to the end. Next, we process the local name. We need to find the position of the first plus sign plus, if one exists. Let's call this plus index. If a plus sign is found, we only keep the part of the local name before that plus sign. Everything from the plus sign onwards is discarded. If no plus sign is found, we keep the entire local name as is. After handling the plus sign, we then need to remove all dots from this modified local name. We can do this by building a new string that only includes characters from the local name that are not dots. Once the local name is fully processed, dots removed, plus sign and its suffix removed, we combine it with the original domain name using the symbol in between to form our final normalized email string. Finally, we take this normalized email string and try to add it to our hash set. The beauty of the hash set is that if the item is already there, it simply ignores the add request, it doesn't add duplicates. If the item is new, it adds it. After we've processed every single email in our input list and added its normalized form to the hash set, the total number of items currently in our hash set will be the count of truly unique email addresses. This is our answer. This approach is much faster because adding an item to a hash set or checking if it exists typically takes constant time on average, regardless of how many items are already in the set. So, for each of the n emails, we perform string operations proportional to its length L to normalize it, and then a constant time operation to add it to the hash set. This brings our overall time complexity down to roughly n multiplied by L, or n times L. The space complexity remains similar to the brute force, n times L, because in the worst case, all normalized emails are unique and stored in the hash set. Let's trace our optimal algorithm with the example input, test.email plus alex@leetcode.com, test.e.mail plus bob.cathy@leetcode.com, test email plus david@lee.tcode.com. We start with an empty hash set, let's call it unique emails. The unique email set is currently empty. We take the first email, test.email plus alex@leetcode.com. First, we find the symbol. The @index is at position 16. So, the local part is test.email plus alex, and the domain part is at leetcode.com. Now, we process the local part, test.email plus alex. We look for a plus sign. The plus index is at position 10. Since a plus sign exists, we take the local part before the plus sign. So, local becomes test.email. Next, we remove all dots from this local part. Test.email becomes test email. Finally, we combine the processed local part with the domain. The normalized email is testemail@leetcode.com. We add this normalized email to our unique emails hash set. At this point, unique emails contains testemail@leetcode.com. Next, we take the second email, test.e.mail plus bob.cathy@leetcode.com. We find the symbol. The @index is at position 20. So, the local part is test.e.mail plus bob.cathy, and the domain part is at leetcode.com. Now, we process the local part, test.e.mail plus bob.cathy. We look for a plus sign. The plus index is at position 10. Since a plus sign exists, we take the local part before the plus sign. So, local becomes test.e.mail. Next, we remove all dots from this local part. Test.e.mail becomes test email. Finally, we combine the processed local part with the domain. The normalized email is testemail@leetcode.com. We add this normalized email to our unique emails hash set. Since testemail@leetcode.com is already in the set, the hash set does not add a duplicate. At this point, unique emails still contains testemail@leetcode.com. Finally, we take the third email, testemail plus david@lee.tcode.com. We find the symbol. The @index is at position 15. So, the local part is testemail plus David, and the domain part is at lee.tcode.com. Now, we process the local part, testemail plus David. We look for a plus sign. The plus index is at position 9. Since a plus sign exists, we take the local part before the plus sign. So, local becomes test email. Next, we remove all dots from this local part. Test email has no dots, so it remains test email. Finally, we combine the processed local part with the domain. The normalized email is testemail@lee.tcode.com. We add this normalized email to our unique emails hash set. At this point, unique emails contains testemail@leetcode.com, testemail@lee.tcode.com. We have processed all emails in the input list. And there's our final result. The unique emails hash set now contains testemail@leetcode.com, testemail@lee.tcode.com. The count of items in this set is 2, which is the correct number of truly unique email addresses. You'll spot this pattern of using a hash set when you need to count unique items or quickly check for the presence of an item in a collection. The key signals are, first, the problem asks for a count of unique elements, and second, you need to normalize or transform items before checking their uniqueness. If you find yourself repeatedly searching a list for duplicates, a hash set is often the answer. The time complexity of this optimal solution is O(n*L), where n is the number of emails and L is the average length of an email string. The space complexity is also O(n*L), in the worst case, to store all unique normalized emails. Now that you understand hash sets, try the next problem that involves counting unique elements. It's a common pattern. Don't forget to like and subscribe for more DSA explanations.